There are two main ideas of Gaussian elimination. The first is to use matrices to save time, to speed up the calculations. The second is what I mentioned at the end of the last video, namely to find a way to convert a general system of linear equations into a triangular system of linear equations, and then use what we did last time, namely back substitution, to finish solving. So let's look at an example of what we're going to be doing. Let's consider the system here. Plus 2z equals 16, 2x minus y plus z equals 9. Today we're going to be showing the equations as well, but usually when you do this, you only work with the matrices. What do I mean by working with the matrices? Well, you can convert this into what's called the augmented matrix. What you do is you take the coefficients and just put them in the matrix. So here, 1, minus 1, minus 1, 2. That's because I have a 1 in front of the x, and minus 1 in front of the y, and minus 1 in front of the z, and a 2 over here. And I put a little bar here just to emphasize that these guys over here are on the right-hand side of the equal sign. On the second row, I have 3, minus 3, 2, and 16. And on the third row, I have 2, minus 1, 1, and 9. And this is called an augmented matrix, or this is, put that back in blue, the augmented matrix of the system. So my goal here is going to be to convert this into a triangular matrix, by which I mean somebody that only has, that doesn't have anything down here, that only has stuff up here. We'll see how this works. So step 1, little 1 here, I'm going to eliminate the x's from equations 2 and 3. Or equivalently, in terms of rows of the matrix, I'm going to eliminate everything in this first column from rows 2 and rows 3. Now, for some point of notation, I'm going to write r sub I for row I, which I'm also going to write for equation I. So the first thing I'm going to do here is I'm going to replace row 2 with row 2 minus 3 times row 1. And doing that, I get x minus y minus z equals 2 for the equation side, because I didn't change that, and 5z equals 10. And I didn't do anything to equation 3, so that's 2x minus y plus z equals 9. But having all these variables around gets kind of confusing. It's a lot to write. So on the matrix side, what I would be doing is, okay, I have 1 minus 1 minus 1, 2. And if I'm going to do row 2 minus 3 row 1, that means that I do, okay, 3 minus 3 times 1, so I get a 0 here, minus 3 minus 3 times negative 1, so that's minus 3 plus 3, which is 0 again, as I would have expected from over here. And over here, I get 2 minus negative 3 times negative 1, so that's going to be a 5, which is what I expected from over here. Sorry, which is what I expected from over here. And over here, I would get 10. And since I didn't do anything to the third row, I get the same thing, 2 minus 1, 1, 9. My next step is to replace row 3 with row 3 minus 2 times row 1. That 2 is so that when I do 2 minus 2 times 1, I get 0. So doing this and going through the same procedure I did earlier, I'm going to get the system x minus y minus z equals 2, 5z equals 10, and y plus 3z equals 5. Or the augmented matrix, 1 minus 1 minus 1, 2, 0, 0, 5, 10, and 0, 1, 3, 5. Let me move things up a little bit so I have more room. The next thing I'm going to do, and this is, I'm going to call it part 2, kind of, sort of, is to exchange rows 2 and row 3, and that's so that we can get into triangular form. To get into triangular form, when I do this, I'm going to get x minus y minus z equals 2, y plus 3z equals 5, and 5z equals 10 for the system. And for the augmented matrix, I'm going to get 1 minus 1 minus 1, 2, 0, 1, 3, 5, and 0, 0, 5, 10. But if you notice, this system here is exactly the same triangular system as in the last video. So this is the same as the last video. So it has the same solution. Namely, 3 minus 1, 2. Now I want to emphasize a very important point here, and that's that each step in each what's called a row operation, each row operation that we made, did not change the solution set. Did not change what's the solution. That brings us to the one last definition before we go on to the next video. Two systems of linear equations are row equivalent if they have the same solution set. So in other words, what we did above is we used a series of row operations to bring our original system of linear equations into a row equivalent system which is easier to solve.